Good morning. So I would like to go on this lecture one, trying to show you um, on a very practical way how to manage um, a couple of databases that it is possible to obtain from recent scientific works. So any Calphad-based software needs databases. Databases may be developed chiefly by experimental work in so if you want to have a look, I think we should try to have a look to those two recent papers that have been proposed by Ben Halstead and his research group. And one paper is about magnesium alloys, and one paper is in a broader and, in a way, um, more, more general and promising topic, which is on high entropy alloys, basically. And this group proposes databases which are possible then to exploit. So I, as we have done with not that many people attending the first online live lecture, we need to open, um, we need, first of all, we need to create a specific activity, which is, I would do it again, create a new workspace. We can choose different options in the software, but basically we will use most of the examples we will deal with. It will be with pan phase diagrams, so working with phase diagrams and application, which is, after all, the basics of the Calphad calculation of phase diagrams, methodology and method in different commercial or open software. So we need to load a database. Um, I would get this one. We will open it, and if everything goes right, we should choose the maximum number of chemical components that we can in the freely available software, which is 3. When then we select components, and in a way, we ask the program there, going up there, so pan phase diagram, we will ask the software to do all the binary phase diagrams. I think the last default settings here, let me check, they have been for weight percent on the x-axis and temperature in Celsius in the y-axis, if I am not wrong, because it's quite early in the morning in this moment, so maybe one coffee was not enough for me. Yeah, seems we are in the mole fraction and Kelvin scale. Um, so we are now generating, practically speaking, the 3 um, binary phase diagram that uh, normally Pandat, like most of anything dealing with phase diagrams, by default it is the alphabetical letter in order. So we will have aluminium, calcium, aluminium, magnesium, and calcium, magnesium. Okay? So we will switch to internet, and I think I need to go back for a while. Banked. Let us go on Scopus. And we will look at our recent that banked is from WTH in Aachen in Germany. He has a very important experience in developing Calphad databases. So the paper that I am looking for, it is on this journal, which is Calphad, and we will have a look at this directly there and go to the publisher. The paper is in collaboration with Mehdi Nouri, and now Mehdi, I think, he is with the software company Thermocalc, and he has done very nice work. And so we would find the database we have just exploited there. I think it will be compressed. I wouldn't take time to that. Well, we can see for the one should download all the supplementary materials here and open them. And unpacking them will result in several files, I think, here. One of those files would be one, which could be this one. So you will have a file name and an extension, which is TDB, Thermodynamic Database. And so this is precisely what we have been uploading just before in our software. We have been downloading from Computer Pandat. And so this is the typical file format of a TDB file, which is actually, for the moment, it is just a text file. And this is quite easy to read for some way, but there are some details that I wouldn't discuss in this introductory and applied course, but you can see that the structure is defining the elements and defining the phases which are relevant to the system, and then you need also the properties of the elements, which are in a way common to most of Calphad databases. Here, you will see that the data have been used and calculated by ab initio calculation. So with a high level computational software, basically developed by people dealing with physics of solid state, you can do some calculations and obtain those databases. Of course, you can, but sometimes you need to check what is going on with the real world, so you need experiment. Nowadays, most of computational metallurgy Calphad's databases have been obtained by means of a very long experimentations, because you need a lot of data and a lot of experiments to get what it is then possible to optimize in thermodynamic databases. So we have been just for our selecting those three components. Let us open, for instance, an open multi-component, so more than three chemical elements databases, database load, this one that I have adapted several years ago, which is basically for light alloys. Let me check which are the elements inside. We will have just aluminum and magnesium. We will not have calcium. What we can do now? We can do something a little different. So instead of asking Pandat to do everything automatically, we will build our binary phase diagram by our own, which is like this one. So I would say that 2300 Kelvin is a little bit too much. Let us go with this one value. So aluminum will be on this Y is here. So 1200 degrees, aluminum 1 mole, 0 moles magnesium, and we are there. Then we go down with the temperature, we go to room temperature, so basically 300 Kelvin degrees. Again, we will stay here in the origin, where aluminum is, fraction is 1 now. And then we go to the X point that would be 0 of aluminum and 1 of magnesium and 300 degrees. So let us see what goes on. Now, we have obtained something which could be equal or not. I have not been checking it before, so let us go into the graph. Let us ask the software copy the copy or copy data. Let's check. Copy data, yes, copy data, possibly. And then let us paste data. So you will see that we have two different situations. So the original graph, the one that generated by Ben Salstedt and Medinori work, is in blue. And now we have been using another open database that you can work out, explore, get the information. So basically in the aluminum side, I would say that everything up to high molar content, not high molar, but medium molar content is enough, but we have slight differences. So which is the important message? It's not that we'll develop, discuss improvements, a selection of one or the other database. This is not up to us for the specific lecture, but we can see that from different databases, we can have different results. I would like to tell you that it is possible to right mouse, label, and get the information on the area that you are selecting and getting the different phases. And so my first introductory message is that if you want to build 2D or 3D phase diagrams with a computational metallurgy software like Pandat, you need a database. You need to select um, the elements that you are interested in, and you need to recover somewhere a database. Having multi-component databases and having good multi-component databases is currently critical, and it's something that is chiefly belonging to the scientific community, but also to the commercial software community. When it is to the scientific community, the databases are open and typically like they are either for free, either done possible to download from scientific journal sites. But when they are developed by companies, typically they are encrypted and they are quite costly. So it depends on you, how many you have, how much time you have to explore things and so on. I believe that on one side, commercial company, they must survive, so they need money, so they need to sell their products, so their software and their databases. On the other side, especially for beginners, it is good to start without any kind of investment from their own or from their own university. So this is a good choice, maybe to start, maybe to consider some potentials of this methodology. In this course, as I have told the guy that's been attending my first live lectures, you can do many other things. For the moment, I would like to tell you that we can use, let us do the same thing that we have done doing this. The icon is this one, which is the binary phase diagram. Let us decide that we don't want to have Kelvin temperatures and we don't want to have molar values. So we go into the options and we would go into Celsius and weight percent. There are also some graph settings here that you can change the character of your graphs and your labels and so on. I think especially if you are younger or much younger than I am, it wouldn't be that difficult to set into a proper way. But the one thing that we need to know, it is switching from Kelvin to Celsius and switching from moles or mole percent to weight or weight percent. Here we are. I think I will just make a solidification simulation and then I would stop. I have made a mistake. I have set the wrong temperature because 300 degrees is not nice. So I think we should to have some real data, room temperature data. So we will use 20 Celsius degrees. So while it is working, we have a look at the 300 Kelvin degrees, and then we will have a look not at 300 Celsius degree Celsius, but room temperature over there. And we have built, again, we can put labels on the main phases, and it will be straightforward. First, you click with the right mouse and then with the left mouse. And graph, you should select this one, labels, okay? Another thing that we can do with the same database, so the one that's open and we've been using, it is and I will insist in this course, a solidification simulation. So let us say that we want to do something like 90% aluminum and 10% magnesium. We want to do a child solidification simulation. It's over there. We will also add legend here somewhere, if it is possible. Is it somewhere? Yeah. And then we will do the same thing, but instead of using child modeling, we will use just equilibrium, so lever rule solidification. Again, we will copy data from the child solidification, for instance, and paste data, so we can compare child with lever rule simulation. And then this is also interesting. Let us go back to the child simulation at first. And then this is quite conceptually interesting. What if I'm using different databases, do you believe I would obtain different solidification simulation results? I believe so, but let us see which are the differences. Remember that the where it is, it should be somewhere in this side of the phase diagram. The situation about phases and lines is not that different. So I would expect, in generally speaking, differences, but going to the details. So let us go back to things, Alsted's and uh, database here. Let us select the two components that we need. So we don't need calcium for the moment. And let us do again this child solidification 90 and 10%. I believe the two things. So let us copy data and paste data. Yes, the two curves are different, but not that much different. So what we will discuss in the next lectures, it could be, is there some possibility to extract more information from this solidification curve? I believe one important thing, it is the slope. So you can see that even though there are differences, the slope is not that different. So how can we calculate with this software the slope? Well, I would do a trial here, so I hope it would work. So we need some extra outputs. So in the tables, we need to add the slope. So as the slope is negative, I would use a minus sign. Then this is in the software the possibility to make the derivative. So double slash and then fs. Fs is the solid fraction. And let us go if it works, because we are now building tables where our data are stored, but then we need to plot some additional graph which would contain on one side the solid phase fraction and on the other, in the y-axis, the slope, so the derivative in mathematical terms. Here we see it. We've been using the last database. So I think we can also, this is just for my curiosity, I don't know if for yours, the slope using, so in the solidification, we can browse there in the workspace the wanted thermodynamic database we have been using in this child solidification derivative. So we have seen the slope of this curve, and then we want to load another database, the more general, I wouldn't say the right database, but another open database, which is the one that we've been using before. So we can load it from here. And then we will use select components, and again, aluminum, magnesium, and then again, this solidification simulation with magnesium 10%. And then we need, again, to check if our extra outputs, so the derivative has been inserted there in the table editor, and possibly the information on plotting the graph has been lost. So we are re-adding the graph. And for the moment, we check if the two slopes, so this is label, let us add a label somewhere, no, a legend somewhere. I wouldn't use negative derivative then. It would take too much. There, okay? And then we will copy data and pass them here. And then we will add, I check if it is possible to add another legend. Yeah. So we will modify it. Well, it doesn't really matter. So we could add more data, we could use this and blah, blah, blah. But we see that comparably, the two derivatives are really so close, especially in the low range of solid phase fraction. So this is solid fraction 0. So it is the beginning of the solidification. And this is full solidification. So phase fraction, solid fraction 1. And we see that the peaks of the two solidification model obtained by two different databases are nearly the same. If I believe the topological behavior is pretty the same, and also the peak is not that different because there is a slight difference in temperature, which is interesting. So I would try to save this workspace, like one lecture one would say magnesium, because the next one, I don't know, today, tomorrow, whatever, I will see. The next one will be on the high entropy. So we have now said that our workspace, we will save everything. Then I would compress everything and leave it available like a zip file. And if you would unzip it, you would obtain it from the internet. I would put information, I think, basically on LinkedIn. For the moment, half an hour is pretty enough for your attention. Um, so let us try to close everything. Remembering you just one thing, that if for any reason you don't have this paper, you can obtain it from um, on on this on this. Never mind. Let us go. Yes, you can. You can in SSRM, and that with the name of the file, as I've been posting by in LinkedIn. Now it would be time to interrupt recording and to say have a nice day to all of you. Okay.